Hi everyone, we are Group 7, also known as Solight Flow, and we're presenting our assigned project titled the Hybrid Lighting System. Our team consists of 4 members. I'm Carlina, the project lead. Along with me are Hari Kumar, Hafizan, and Sean. Throughout the semester, we've worked together to design and plan a renewable lighting system that combines solar and wave energy aimed at supporting rural and coastal communities with limited electricity access. Let's begin by highlighting the core problem that this project aims to address.
Hi, my name is Sean Aronsin. My metric number is BK22110269. I will be presenting about what our project is, who will be using it, and where it will be used. The first one is what our project is. Our project is a hybrid lighting system that utilizes solar energy and ocean wave energy. In the market, lighting systems that utilizes solar energy are widespread. However, the main weakness is weather. When the weather is cloudy, the sunlight is not strong enough to fully energize the solar panels utilized by the lighting system. Therefore, our innovation is by adding a secondary energy generator which utilizes ocean energy. The second is who will be using it. The one that will be using our project is students living in rural areas, especially near the oceans. They receive a limited amount of electricity and often depends on candles and kerosene lamps to study. So our project aims to help them in their study session. The third is where it will be used. Our project will be installed in students' houses, specifically at their study desk, to help them for their study sessions during night times, so that they can see and learn without depending on candles and kerosene lamps. I will also be explaining about stakeholders. Stakeholders are those who are directly or indirectly involved with the project. They can be the user or those who are supporting the project itself. The first stakeholder is the students. They are the main user of the project. The second one is Dr. Herwan Shah. He's the one who acts as our academic advisor and supervise the project itself. The third one is the engineering faculty of UMS. They provide the internal components such as resistors, capacitors, and all the internal components to help lessen our burden in buying the components itself. In this slide, I will be presenting about how the idea of the hybrid lighting system was developed. There are several thousands of houses in Sabah and Sarawak, especially those who are in rural areas and those who are living near the ocean that does not get reliable grid and connectivity. This is due to the challenging terrain and high cost in creating the grid extensions. Some of them already implemented solar panels to act as a energy generator. However, due to Malaysia's monsoon climate, which causes high wind and cloudy weather, effectiveness of solar panels are not reliable. This causes these communities to continue to rely on expensive diesel generator and kerosene lamps. There are one possible solutions that we have found. That is by using ocean wave energies. Due to the communities living near the oceans and due to Malaysia's monsoon climate, which offers high wind, causing high oceans waves activities. Therefore, we found that by utilizing these ocean waves to create kinetic energies, which in turn will be turned into electricity, can be used and combined with solar panels to create a more stable, renewable energy source for the communities to use, especially for the students that we are aiming to help.
Hi, Assalamualaikum. My name is Muhammad Hafizan bin Soni and my number metric is BK22110217. So this is a slide how our hybrid lighting system project solves the problem. So we have four problems and four ways we solve this problem. So for the first problem is unreliable electricity supplies in rural or coastal areas, which often leads to inconsistent power. So our solution is we directly address this by combining solar and wave energy to ensure continuous power even in bad weather. The second one is the current reliance on fossil fuels lead to energy high costs. So our projects directly solve this by uh, leveraging free renewable energy source and low power LED light to significantly cut long-term costs. And the third is no lighting at night during blackout or low sunlight because this is directly impacts safety, security, and daily activities after dark. So our project resolve this by including battery storage to supply energy during night or low generation times. And finally, boosted energy due to lack of intelligent energy management. So our project is equipped with a smart control that manage and optimize energy usage. So this intelligent management ensure that every bit of energy is used efficiently, reducing waste, minimizing benefits, and contributing to overall sustainability. Alright, now is the block diagram. So this diagram is crucial because it shows how energy flows from our to renewable sources, which is solar and wave, and all the way to the LED lighting. S- So for the first one is on the far left, you can see energy generation blocks for solar panel and wave energy generator. So this is our primary sources of clean energy. So and then moved into the energy conversion and switching module. This module intelligently combines and manages the power from both sources. From there, the energy goes to the power control unit, which regulates the power flow, and then directly into the battery charging and storage unit. So this is our energy reservoir, ensuring the continuous power supply even when the generation is going low. So finally, from the battery, power flows to the lightning output module, which include our LED lighting unit providing the illumination. So this diagram clearly illustrates the complete energy journey within our system. So below that we have our system behavioral module. This diagram is equally important as it outlines the logic flow for source, switching, battery charging, and lightning operation. So looking at the flow, you can see the decision made based on sunlight and wave energy availability and how the system prioritizes charging and the battery and how it ensures the LED lights are powered consistently. For example, it shows the condition under which we switch between solar and wave or draw power from the battery when both sources are is insufficient. So together, these two diagrams provide a comprehensive overview of both the physical components and operational logic that makes our hybrid lighting system robust and efficient.
Hi, my name is Harikumaiko Kumarasan. Number is PK22110130. For my part, I will explain about the design project. As you can see here, this is our project finalized design that we choose. A little bit explanation. We're using two input, which is one is from the solar panel and one is from the wave converter, which connected with the controller, and the controller itself connected with the battery, and one go to the table lamp. So basically in the controller we put a one switch that we decide either we're using a solar energy or wave energy, also combination from the solar and wave energy to power up the battery. Once the battery is fully charged, it will provide the energy go through the table lamp itself. So basically that's our design that we put here. And for advantages and disadvantages, we can see here advantage: compact all-in-one unit, easy to mount, better protection against marine moist and rust, improved safety whether a few external voids means a low risk of short of electric circuit, clean modulation assembly, which is ideal for a rural area deployment, which is we know that this project we are targeting in an area, rural area, which we know also known as Rumah Atas Air. That's our main target area. And so in that area we know that it's gonna have a risiko that we have rust moisture from the seawater itself. So we have to overcome with that thing. And disadvantage is a less convenient access to the controller, since we're putting the controller inside the table lamp, because for safety reason for the user, which is our user is mainly student that are going to use table lamp in the night time. Require careful internal heat management. Full unit replacement needed if the external board fails. More difficult to modify or customize after the assembly, because our controller or the whole product is inside the table that we are planning to do it. So why our project is important? One is better safety compared to the traditional method we're using for nowadays is candle, the kerosene oil that we're using. But compared to that, our design is more safety, far more safety, I can say that, and simpler installation, compact and tidy, temper resistant and reliable operation. So that's from our design project itself. Thank you. For the next part, I will explain about comparison component and a cost. For the cost component, we are choosing a 4 main component that I feel like I want to talk about, and with alternative to two ways, and why I choose the component and a justification for that. For the first one, I charge controller that we discussed about in the design project earlier. We're using a PWM10A because it's a cost efficiency option compared to 2 others, and also a capacity for prototyping. For the current sensor, we are using ACS7125 ampere. Why? Because it's a provide electrical isolation and easy interfacing, and ideal for a simple prototyping. For the voltage sensor, we are using voltage divider because it's low cost mainly and accuracy enough for monitoring battery and voltage in a basic energy system. For the battery, we're using a 12 volt 7 AM AGM battery. Why? Because compared to 2 others, one is 9 and one is using a gel type. But we prefer to use AGM because why? Because the battery is a location availability and supports, and compared to the how many hours the student using, and the safety also required to see is why we choose AGM compared to a gel type. For the next part, I will talk about BOM, which is billing of material. For overall total component cost, we cost us 275 ringgit, including a wave energy converter that we use, that we say that we are using from the FYP student, but still have to put 30 ringgit because we are kind of modifying a little bit for our combination hybrid lighting system. For development and support cost breakdown, we're using a development cost which is about 60 ringgit for testing, prototyping, printing, all such kind of thing like that, and the total project cost is 335 ringgit. And the cost comparison compared to the traditional method we're using is candle and kerosene lamp, which is cost us around 3 ringgit per pack and 8 ringgit for a liter, like that, compared to 335 for one time installation. It may be a bit costly compared to those 2 methods we can see here, but however, I think safety wise is quite more important, because in this project our hybrid lighting system is far more secure, and also safety risk low compared to the candle and kerosene lamp, because it both got fire hazard, which is concerned about. So I feel like our project is only one time and another is maintenance only. So I feel like our project is far more competing with other traditional method. That's why I feel like our project is kind of in this matter, our project is far more safety and competing method. Thank you.
Hello, my name is Karina Napchili, matrix number BK22110036, and I shall be presenting about our project timeline. So here in this slide, here's our full project timeline planned across 14 weeks. As you can see in the Gantt chart, the schedule is broken down into key phases: planning, design, component selection, prototyping, integration, testing, and final reporting. For this semester, our team focused on completing weeks 1 to 6. That includes finalizing the project topic, conducting background research, creating system block diagrams, and selecting all required components based on performance and cost. Each phase was carefully sequenced based on dependencies. For example, prototyping can only begin once the system design is finalized. programming and testing are scheduled for next semester following this structure. We used a modular workflow, meaning each team member handled a specific subsystem. This helped us stay efficient and complete the design phase on time without delays or overlap. By planning early and assigning clear milestones, we've set ourselves up to start physical prototyping right away in the next phase. As shown in this table from our proposal, our group divided responsibilities based on individual strengths, and I took the lead in project planning, timeline development, and overall project coordination. Harikuma focused on the Arduino logic and wave energy subsystem, including component wiring. Hafizan handled the solar panel setup, circuit design, and testing. Sean worked on the battery and lighting system and also helped with circuit installation and development. My job as project lead was to make sure everything fit together from the early planning stages through system development while ensuring our progress aligned with the Gantt timeline shown earlier. By assigning clear roles early on, we avoided overlap, worked in parallel, and completed the design phase up to week 6 as scheduled. In short, this wasn't just a team effort, and it was a coordinated strategy built around our timeline, and that's how we kept the project on track.